Welcome, welcome everyone. Welcome to the eighth part of our series on analog electronics. We have already covered semiconductors, PN junction, rectifiers, transistor configuration, and operational amplifier. The link to those tutorials are provided in the description below. I would particularly request you to go through the tutorial on operational amplifier as it would help you to understand the contents of this particular tutorial. In the previous tutorial, we have done the applications of op-amp as the inverting amplifier, the non-inverting amplifier, voltage follower, summing amplifier, and the subtractor. In today's tutorial, we are going to look into integrator, differentiator, comparator, and zero crossing detector. Let's move on to our first topic, integrator. In the integrator, the feedback is provided through a capacitor C. The current through it is denoted as IC. The input current is IN, which flows through a resistor RI. The input voltage is Vin and the output voltage is Vout. All the symbols have been written in lower hand case. In the previous tutorial, you might have seen that the voltages and currents were denoted in the upper hand case, that is capital V and capital I. It is because the integrator is a AC only circuit, and for such circuits we denote the notations by small hand letters. So if we provide a sine wave, that is the red one, we receive the cosine wave as the output, that is on the right hand side, the blue wave. Let us look into the mathematical expression of an integrator. Now, the current through the capacitor is equal to the input current as no current flows through the op-amp. So, IC equals to IN. The input current IN is nothing but Vin by Ri, or from the previous equation, the current through capacitor IC is also Vin by Ri. The charge on the capacitor Q is the integration of the charge through the current through the capacitor over a period of time dt. Plugging the values, we receive Q equals to 1 by R integration V in dt. The voltage across the capacitor is 0 minus V out equal to Q by C. Q by C is the voltage drop across the capacitor. Therefore, V out equals to minus Q by C, which gives us the equation of the output voltage, that is V out equals to minus 1 by RC integration of V in dt, that is the output voltage is the integration of the input voltage, and hence the circuit is called the integrator. We'll look into a very special case where we will provide a steady voltage. As you can see, if you provide a steady voltage like this, the output is a downward ramp. That is, with passing of time, the output decreases from a maximum to a minimum value. If you have the negative steady input voltage, then you get a positive going ramp. This voltage is called the ramp voltage, and it gives integrator a use as the ramp wave generator or the triangular wave generator. For that, we provide a continuous square wave as input to the operational amplifier, and we receive a triangular wave as the output. The integrator is also used as a wave shaping circuits and is also a component of the analog to the digital converters. Now, at 0 Hz, the feedback capacitor behaves like an open circuit. So, there is no feedback from the output to the inverting input of the op-amp. The circuit behaves like an open loop inverting amplifier with very high gain. This will result in the saturation of the op-amp voltage. As the input frequency increases, the capacitor gets charged. By connecting a feedback resistor RF, which is nearly equals to 10 times that of the input resistance Ri, in parallel with the capacitor, a precise closed loop voltage gain can be obtained. All integrators have a critical frequency Fc, which is equal to 1 by 2 pi C into Rf, below which they do not perform proper integration. That is, we have to provide an input frequency greater than this value for the integrator to behave as an integrator. Below this frequency, the circuit behaves as a simple inverting amplifier and no integration occurs. This is the practical integrator that is used in all op-amp circuits. Let's move on to the next topic, differentiator. The differentiator circuit is an exact replica of the, or rather a mirror image of the integrator circuit, in which the input is provided through a capacitor and the feedback is a resistor. Whereas in case of an integrator, the input was provided through a resistor and the feedback was through a capacitor. So the current through the input is In and the current through the feedback resistor is IR. If we provide a sine wave, we again receive a cosine wave. Let us look into the mathematical expression. Again, In is equal to IR. The current IR through the resistor RF is nothing but minus of V out by RF. The charge on the capacitor Q is nothing but C into the input voltage. The input current is given as dq by dt, or plugging the values of the input current, we get the equation minus V out by RF equals to d CV in by dt. The output voltage V out equals to minus of CRF dVin by dt. So this is the equation. You can see that the output is the differentiation or the derivative of the input voltage. Let us again consider what happens to the steady voltage. For a positive steady voltage, we get a spike kind of a voltage rising from the lower extremity to 0. For a negative steady voltage, the spike arises at the positive extremity and comes to 0. So if you provide a square wave, you receive this kind of a spiked outform. The spiked output waveform. Let us see what happens when we provide a triangular waveform to it. So again, we provide a negative going ramp, we receive a positive steady output voltage. If we give a positive going ramp, we receive a negative steady voltage. That is, if we provide a triangular wave, we receive a square wave. So the differentiator can produce a spiked wave when a square wave is provided and produces a square wave when a triangular wave is provided. They are mostly designed to operate on triangular and rectangular signals. They also find application as wave shaping circuits and are used to detect high frequency components in the input signal. The differentiator also suffers from the same frequency problems as the integrator, and to overcome it, a resistor Ri is connected in series with the input capacitor and a capacitor Cf is connected in parallel with the feedback resistor. This solves the problem and it gives a stable output at most frequencies. The differentiator among all op-amp circuits is the most unstable one and is not generally used in analog computers. Let us move on to the next topic, comparators. Comparator is basically a non-linear op-amp device in which the negative feedback is not used. It is a circuit configuration that compares two voltages and indicates which one is larger. There are two types of comparators, the non-inverting comparator, which is on your screen, and the inverting comparator, which we will see in the next uh, slide. So when the input voltage V in, which is this one, which is provided to a non-inverting terminal, and it is compared with the reference voltage Vref, which is this steady value, and it is provided to the inverting terminal. When the value of the input voltage V in is greater than the reference voltage Vref or V reference, the output voltage V out goes to positive saturation. This is because the voltage at non-inverting input is greater than the voltage at the inverting input. When the value of the input voltage V in is less than the reference voltage V reference, the output voltage V out goes to negative saturation. This is because the voltage at non-inverting input is smaller than the voltage at the inverting input. Thus, output voltage changes from positive saturation point to negative saturation point whenever the difference between V in and V reference changes. The comparator can also be called as a voltage level detector, as for a fixed value of V reference, the voltage level of V input can be detected. We have seen one example with the sine wave. Let us see how it behaves with the triangular wave. That is the input wave, and this is the reference wave, and this is the output wave. As you can see, the output again changes between a positive saturation and a negative saturation. Let us move on to the inverting comparator. In this comparator, the input is provided to the inverting terminal and the reference voltage is provided to the non-inverting terminal. This is our input voltage, this is the reference voltage, and this is the output voltage. Here, the positive V saturation is achieved whenever V input is less than V reference, and negative V saturation is achieved whenever V input is greater than V reference. Let us repeat for the triangular waveform as well. The output waveform is same as that in the case of the sine wave. One interesting use of the comparator is the zero crossing detector. In the zero crossing detector, what we have done is the inverting terminal is grounded and the non-inverting terminal is provided the input. Let us see what happens when a sine wave is provided to this kind of a zero crossing detector. As you can see, whenever the input voltage is greater than 0 volt, because the reference over here is 0 volt, you get a positive going saturating voltage, and whenever it crosses 0, the input wave crosses 0 in the negative direction, that is V in is less than 0, you get a negative saturation. So whenever a zero crossing detector changes its saturation state, you can say that the input voltage has crossed 0, and that is why it is called the zero crossing detector. Let us repeat the same for the triangular wave. The output waveform is as same as in the previous case. Let us move to the inverting zero crossing detector. Here the only change is that the input is provided to the inverting terminal and the non-inverting terminal is grounded. Let us give the input as over here. As you can see, whenever the input voltage is greater than 0, a negative saturation is obtained, and whenever it is less than 0, a positive saturation is obtained. Let us repeat for the triangular wave. The output waveform is the same as in the previous case. So in the last 8 tutorials, you have gone through various aspects of analog electronics. We will end the series here. I hope you have liked the series. I believe you have liked, shared, and subscribed. And if you have not done that, please do it. That gives us encouragement to provide you with even better video content. Soon we will be here with another video tutorial on a new topic in physics. Till then, stay healthy, stay safe. Thank you.